Hello, am I audible?
Yes.
Okay. Okay, so good evening. Uh, I hope you have solved the assignment questions.
Good evening.
Yeah, good evening. Okay, we'll wait for one or 2 minutes then. Could you solve any questions from assignment? Hello? Okay, we'll start with the class. So last time we have discussed the basic conduction laws and then some brief introduction on convection, radiation, and all this. And we have seen how to solve problems on Fourier's law, and then we have also seen the composite wall problems, how the resistance uh, diagram can be drawn and these problems can be solved. Okay, so today we are going to see the next lectures you might have seen for this week, which the professor has taught. So today we will be, so you can see my screen also, right? So today we will be talking on those, we'll be discussing problems on the content which is being taught in this week, like the conduction. In last class we have done about the one plane in I mean sorry in a single, I mean in a plane structure, 1D conduction in a plane wall or planar structure. So this week we'll be doing the same thing, the same conduction in radial surface, that means the cylindrical coordinates, or maybe one or two examples I have included for the spherical problem also. And then the professor has also taught on the extended surfaces or the fins. Okay, so we'll before moving on to the next set of problems, last class I have said that I'll include a problem on this contact resistance. So we'll start with that. Okay, we'll start with the contact resistance problem. So this is the first problem. An aluminum plate of 25 millimeter thick, around the conductivity is given to be 235 watt per meter Kelvin, is attached to a copper plate with a thickness of 10 millimeter. So already in the figure it is given. This is the aluminum plate, and it is of the thickness is given to be around 25 millimeter. Then this has a thermal conductivity of 235 watt per meter Kelvin. This is attached to a copper plate with a thickness of 10 millimeters. So this is the copper plate actually. And this is 10 millimeter thickness is given for the copper. Okay, the copper plate is electrically heated to dissipate a uniform heat flux of 5300 watt per meter square. So already this plate is heated, it is electrically heat is supplied, and it has a flux of around 5300 watt per meter square. The upper surface of the aluminum plate is exposed to convection heat transfer in a condition such that the convection heat transfer coefficient is 67 watt per meter square Kelvin. So this upper part of the aluminum plate is exposed to air, or there is there is convection heat transfer going on in this place, and the convective heat transfer coefficient is given to be around 67 watt per meter square Kelvin, and the surrounding room temperature. Okay, you want to get these questions, you solve it. It's better you solve it right now. There will be some questions for your assignment also. They might have given you some assignment questions, you solve those and you have to submit. But these questions, if you solve it right now, then it will be better. And also, if you cannot solve it, these videos, I mean, you can hear me, right?
Yes, yes.
Yes. So you can see, I mean, I'll upload my this video, I mean, my this teaching session video in YouTube. You can watch it again, and then you can see
Okay,
the problem again.
okay. Thank
Yeah.
you.
So, and the surrounding room. So try to solve these problems right now. Yeah, then it will be helpful. I mean, you can later solve those assignment questions as soon as possible. Then other surfaces of the two plates are insulated. That means only this surface is conducting or it's convecting, and this surface is conducting, and all other parts are all other these parts are insulated. This is insulated, this is insulated, and on top and on below it's all are insulated. Only at the upper and below surfaces, below means only this one is conducting. So whatever heat actually the electricity is, I mean the electric power is generating through the copper wire, that heat itself it is getting conducted to the aluminum plate. So if the surface of the copper plate is attached to the aluminum plate has a surface temperature of 100 degrees Celsius, that means it's not the temperature of the copper plate, but it's the temperature at the interface between the copper plate and the aluminum plate, that is given to be 100 degrees Celsius. That is this one. Okay, the interface that is 100 degrees Celsius. So determine the thermal conductance of the aluminum or copper interface. So here it is given to determine the thermal conductance. So what is thermal conductance? Already we have talked, we have discussed on contact resistance. Okay, so conductance is simply, if Rc denotes thermal contact resistance, then you can denote with Hc. Hc, which is given by 1 by Rc, is the thermal contact conductance. Okay, So thermal contact conductance is just the reciprocal of resistance. Conductance is the reciprocal of resistance. So if RC is a contact resistance, so AC, which is given by 1 by RC, is the contact conductance. Now, to solve this problem, what we can do is, again we'll draw the resistance diagram for this. So here the temperature, here it is given to be around T1, that is 100 degrees Celsius in the interface, and the temperature at the surface is given to be around 20 degrees Celsius. That means the outside surface. So in between these two temperatures, what are the resistance which you encounter? Okay, so if we start from the air, there will be convective resistance, that is 1 by HA. Then there will be this aluminum plate resistance, that is L by Ka. Aluminum plate resistance is a conductive resistance due to conduction. And then another resistance is present due to the this interface between the aluminum and copper, that is known as the contact resistance. So that is given by Rc. So here the temperature is 100 degrees Celsius, and here the temperature is 20 degrees Celsius. Okay, so how do you it's the same problem for the resistance problem. So Q is given by delta T divided by total resistance R. Okay, R total, and delta T is given by 100 minus 20. And what are the resistances? RC plus 1 by HA. 1 by H is 67 into, you can just write it A because the area is not given, and then it is L. L means 25 into 10 to the power minus 3. Okay, 25 into 10 to the power minus 3 divided by Ka. K is 235 A. So you don't know A. And the Q which is given, that is 5300 watt per meter square. So this is also Q double dash. That means this is, if we include A, then it should be QA. So if we write in terms of flux, it should, if we should multiply it by area. And here the flux is only given, that is 5300 watt per meter. How do you know it is flux? It is divided by meter square. That means it is divided by the area. So it is, so if we find out RC by A, I mean, since all other resistances have uh, the A and unknown, so you can even write RC by A also. So here, this is, you can just cancel out all the A, okay? Then from here you can directly calculate the RC. Here Q is given as 5300 watt per meter square. So you can all other values you know, then you can get directly RC. Can you quickly calculate what is the RC? Since I don't have space here, can you tell me what is RC? 'Have you calculated?
66.25 something.
And what about the HC? HC is just 1 divided by RC.
0.015094 something.
Okay, you just recheck the calculations because I have got something else. HC will come out to be around 16,000 watt per meter square Kelvin. So I'm just erasing this one. Did you take the thickness as only 25? Consider it to be, I mean, just convert it into meter. 25 into 10 to the power minus 3. How much do you get? This is around 11,000 something. So the answer will be around in some power of 5, 1 point into 10 to the power 5. So it will be like this. Okay, so just check the calculations. Can we move to the next question? I mean, so this is just a brush up of the formulas of whatever this week the professor has taught. So this is the this is the generalized equation. I don't know why it is coming here. Okay. This is the generalized equation. K del square t plus q dot equal to rho cp delta t by delta t capital T by delta small t. So uh, this was general heat balance for anything, for any system you can use. It is just in minus out plus generation equal to the accumulation term. Now for planar coordinates, we have seen the Cartesian coordinates. We have seen last day itself how the t is how the function of t looks like. But in spherical, I mean in radial coordinates, it looks like this. Heat balance looks like this, and if for radial coordinates, you can just the t function looks like this. Okay, this is given del square. The Laplacian of t is given as 1 by r del r of r del t by del r plus 1 by r square del square t by del phi square plus del square t by del z square. Okay, for cylindrical coordinates. Uh, so if you consider it as 1D, 1D conduction in radial direction only. Then the these two terms get cancelled out and you get only this, only the first this term you get. Okay, and if you solve this already, you might have seen in the lectures, then you can get the temperature profile as this: T is equal to T1 minus T2 divided by ln of R1 by R2 into ln of R by R2 plus T2. And then the Q, the heat conduction or the heat rate, you can determine by this formula: 2 pi R into L into K into T1 minus T2 divided by R ln of R1 by R2. And resistance is just the um, resistance is equal to T2 minus T1 divided by QR, or QR is also equal to T2 minus T1 divided by resistance R. So both of them are reversibly proportional. So this is equal to resistance comes out to be around ln of R1 by R2 divided by 2 pi KL. And so these are the formulas which will be, maybe today we might be using this. So in just brief, I have given you in just one page what formulas and all will be required. Okay. So for the first problem, we see that a steam pipe of 0.12 meter outside diameter is insulated with a layer of calcium silicate. Okay, so what does it mean? It means there is a steam pipe. Okay, there is, so this is the outside diameter. If this is the outside diameter of a pipe, okay, D naught is DO is given as 0.12. So R naught, or the outside radius, will become 0.06 meter. So this is insulated by a layer of calcium. So this is the insulation of calcium silicate, and this insulation is 20 millimeter thick. Delta T is given as 20. This is small t, okay? I mean, this is not temperature, it is thickness. 20 millimeter, which is equal to 20 into 10 to the power minus 3 meter. And its inner and outer surfaces are maintained at Ts equal to 800 Kelvin and Ts2 is equal to inner and outer. So if this is the cylinder, its inner surface, that is this one, its inner surface is maintained at 800 Kelvin, and the outside surface, outside this cylinder, this outside part is maintained at temperature Ts2 is 490 Kelvin. Then what is the heat loss per unit length? That is Q dash of the pipe. And calcium silicate, the thermal conductivity is given to be 0.089. So in the previous, uh, here we have seen that the T, the formula of T, it can be or the Q. They have asked to find out what is Q. So the Q formula is also given. You can directly use it. So Q is equal to minus 2 pi KL T1 minus T2 divided by ln R1 by R2. Okay, so just find out what is q. Everything is given. So if you take the L here, they have asked to find out what is the q per unit length. And length is also not given. So just find out per unit length. Q by L is equal to minus 2 pi k T1 minus T2 ln R1 divided by R2. If we take this as T1, the inner temperature as T1, the outside temperature as T2, so the inner radius will be take it as R1, and the outside radius take it as R2. So inner radius we already know what it is. It is given in the question. From the diameter it's given 0.12 meter. So inner radius will be 0.06 meter. Okay, so R1 is 0.06 meter. And what is R2? Can you tell me what is R2? R2 is,
10
yeah,
mm, 10 mm.
10. What did you say? Can you repeat?
Wait, ma'am, I will say in 2 minutes.
Uh-huh. Are you getting the diagram? Is the diagram clear?
Yes, yes, yes. 10 mm.
10 mm. I'm asking about the radius. Radius of the outer circle. This circle, this bigger circle. What is the question given? A steam pipe of 0.12. I'm drawing only the cross section here, okay? For for your understanding. A steam pipe of 0.12 meter outside diameter is insulated with a layer of calcium silicate. That means if this is the outside diameter of the pipe, this is the outside diameter of the pipe, this one you can see, this if this is the outside diameter of the pipe, then it is insulated with uh, a layer of calcium silicate. This one, this is calcium silicate. So what is given is the outside diameter is 0.12 meter. That is, this whole one is a diameter, right? Whole one is a diameter. Is given as 0.12 meter. And so what will be the radius of this? If the diameter is 0.12, the radius will be 0.06. 0.12 divided by 2. This is equal to 0.06 meter. Okay, the inner diameter. This is R1. And what will be the this R2? If this is the inner diameter is 0.06, the R2, that is the outside diameter. Sorry, outside radius. R2, how much will it be? The thickness is already given, right? Thickness of calcium silicate. This is 20 millimeter. That means 0.02 meter. So R2 will be 0.06 plus 0.02, that is 0.08 meter. Did you get it? Did you get this point?
Yes, yes.
Yeah. So you just have to the radius, the outside radius, you can just get it by adding the inner radius plus the thickness of the whatever insulation is given. Okay, so it will come out to be 0 0.0. This is R2. So outside is denoted by 2, inside is denoted by 1. So if you just incorporate all the values here, minus 2 into 3.14 into K is around 0.089 into T1 minus T2. 1 is inside, so inside 1 is 800 minus T2. 2 is outside, outside temperature is given to be around 490. And then ln of R1 by R2. R1 is the inside temperature, inside radius, that is 0.06 divided by outside radius is 0.08. So just calculate how much is the, which option it is coming.
Option B. कैमरा नहीं चल रहा?
Option B, okay. Option B is right. So you got this problem, right? Okay, we'll move to the
Yes,
next.
ma'am.
Yeah. So we'll move to the next question. So here again, a stainless steel tube is used to transport a chilled pharmaceutical, has an inner diameter of 36 millimeter and a wall thickness of 2 millimeter. So this heat transfer problem, here itself you can see where which industries and all this is used. It's used in industries, pharmaceutical industries. So it is used to transport, maybe for chilling purposes, for heating purposes. So all this is an example of heat transfer industry. So it is used to transport a chilled pharmaceutical in and it the tube has a inner diameter of 36 millimeter. This is radius, this is the diameter. Okay, this is 36 millimeter and a wall thickness of 2 millimeter. Again it has wall diameter. Okay, the pharmaceutical and the ambient air, this is not the insulation here. They have not talked anything about insulation. This is only the wall of the stainless steel. The wall of the stainless steel itself is of 2 millimeter thick. The pharmaceutical and the ambient air are at temperatures of 6 degrees Celsius and 23 degrees Celsius. So the pharmaceutical is inside. Since it is used to transport the pharmaceutical, the thing is inside. So for the any medicine you want to carry or anything maybe, so it is flowing inside. So the inside air or the inside pharmaceutical temperature is, if you take it as T infinity 1, it is 6 degrees Celsius, and outside it is T infinity 2, it is 23 degrees Celsius. Okay, this is not the temperature of the stainless steel, but it is temperature of the surrounding. Outside it is air and inside it is the pharmaceutical. Okay, respectively, while corresponding inner and outer convection coefficients are 400 watt per meter square Kelvin. So inner convection is around H1 is equal to 400 watt per meter square Kelvin, and the outside outside one is the H2 is si sorry 6 watt per meter square Kelvin. What is the heat gain per unit tube length? So again you have to find out Q dash, that is heat transfer rate per unit length. Stainless steel, this Ks, heat conductivity, is given as 14.2 watt per meter Kelvin. So just find out what it should be. Do you have any idea how to proceed? It is not the same as the previous one. In the previous one, they have given the temperature of the uh, that cylindrical body itself. But here they have not given the cylindrical this surface steel surface temperature. They have not given. Rather, they have given the outside temperature. That means the ambient air and the inner fluid which is flowing inside. That temperature they have given. So how will you proceed in this? So in this problem can be done again by using the resistance problem which we have followed in last class. So there are how many resistances? There are three resistances, okay? One is the inside fluid resistance. Another one is the this this stainless steel itself, the resistance for this stainless steel itself, and the next one is the resistance in the outside air, okay? So this is inside one, T infinity 1. This is outside T infinity 2. So first resistance is the inner convective resistance, that is 1 by H1A. Okay, here in planar surface, in rectangular wall or in planar wall, the area does not change. But here in this problem, like in last class, whatever problems we have solved, all this area have remained same. But here the area of heat conduction, this is different. Why it is different? You got it right, because it is radially, the heat is radially coming out. So in the in the from inside is it is coming out to the outside ambient air. So the first radius is very small, and then the next radius is bit bigger, and then it keeps on the radius keeps on increasing. That's why the area keeps on changing from inside to outside. So whatever area is here in the inside, that is, let us consider it as A1. And then the next one is the conductive resistance due to that steel, that is L by Ka. Maybe this is A2. Okay, the next one is the okay. So planar, I mean for cylindrical resistance, for conductive resistance, you get by this formula ln r1 by r2 divided by 2 pi kl. Okay, ln r1 by r2 divided by 2 pi kl. So this is the formula which we'll be using for the resistance for the conduction part. So you cannot use this formula here. Instead, you'll use this formula.
Ma'am, the 1 by H1 into R1 and 1 by H2 into R2,
It's
it
not
is
R,
correct
it's
or
A,
wrong?
A. 1 by H1 into A1 and 1 by H2 into A2.
Ma'am, but I have considered in previous problem 1 by H1 into R1 or 1 by H2 into R2. So it will be wrong or correct?
For this question, for which question are you
No,
talking?
no. Assignment questions. Assignment questions.
Okay, assignment questions. Hi.
Yes.
See, in this, so it should, the main formula is A1. From A1, if this A1 will come out to be 2 pi R L L1 like this. This is the formula of A, right, for cylinder. 2 pi R into L. So anyhow,
Ma'am, there are, we consider, at that time we consider R1 or R2 in case 1. And when we solve 1 by S2 into E2, then 2 pi R2 into L2. Uh, this we take in this problem.
I don't know. I have not seen the assignment questions, but the formula, the resistance formula for any resistance formula, this is the this even in last class also we have done, right? 1 by HA. This is the resistance for convection, and the for conductance conduction it is L by Ka. You cannot change this. This is the formula for resistance. But for simplification, you can just now even while solving this problem also you have to break down this A. A will be written as 2 pi r. How can you directly calculate the area? You have to write this formula for area, 2 pi r into L. So here the it for A1 it will be R1, for A2 it will be R2. Okay, then maybe you have done some simplifications, some cancellations here and there. Then that's why it might be H1 R1 and H2 R2, like that. Are you getting? But for resistance, the you cannot change this. The resistance is always 1 by HA for convection, and for conduction it keeps on changing, whether it is uh, rectangular wall or whether it is cylindrical wall or spherical wall. Did I answer your question? Or you may write in the chat box what you have written, what you have spoken. So from all these terms, the L is constant. I mean, yeah, you can just take out the L and that will get cancelled out with this L. So you don't need to know what is the length in this case. So directly find out what all the values are given here. T infinity 2 is 23 degrees Celsius. T infinity 1 is 6 degrees Celsius. Then H1 is 400 watt per meter square Kelvin. 2 pi R1. R1 is R1 is the, yeah, so diameter is given, right? So R1 is 0 point. If diameter is 36 millimeter, R1 should be 18 millimeter, and 18 millimeter is 0.018 meter. Okay. And the same way you have to calculate what is the R2, that is outside diameter, because of the wall thickness. Okay, so R2 will be 0.018 plus the thickness is given to be 2 millimeter, that is 0.002. It will come out to be 0.02 meter. So you know R1, you know R2, you know H2, you know K. K is also given. It is K of the steel is 14.2 watt per meter Kelvin. Please calculate this and tell which option did you get. Which assignment problems are you solving? Are you solving the first one or the second assignment problem? The second week or the first week?
Second week.
Okay, okay. So what they have asked to find out? They have asked to find out the heat transfer, I mean the heat gain, heat loss, heat rate, or the overall heat transfer coefficient.
The heat loss.
Heat loss.
Yes. There are two conditions are given in this problem. But in first condition, terms are given for mm, negligible. Some conditions are given that we take in ma'am question number in assignment question number 5. This is problem. You can check after this with how it is, how can we solve it solution,
Okay,
or how to.
I'll check later.
Okay, okay.
Yeah, yeah.
Thank you.
But if it is, if the, what to say? Some, if you have made some simplifications like this, like here you can cancel out the L, you can cancel out, then the formula might change, but the resistance formula will not change. It should always be, the, what will be the unit for resistance? Meter by space. It will come out to be K by watt, I think, Kelvin by watt around. So it will always be Kelvin by watt. That assignment you have, you'll, I think you'll submit more. First assignment, I think you should submit by 4th, right? So we'll get some time to discuss on that. Okay, now tell me what is the answer for this.
Option C.
Yeah, option C is right. Did you get this problem? How it is solved using the resistance networking?
Yes, yes, yes. Yes, yes, yes.
Yes.
Thank you.
Yeah. Then next one I have taken an example for spherical shaped structure. Okay, the wall of a spherical tank of 1 meter diameter contains an exothermic. Okay, before this we will just see some, I mean, in the lecture series might be the professor has not shown for the spherical system the temperature profile and all. So for that, so what you can do is you can take the, just like in the previous case, there is a cylindrical, this is the, this t which you can, this delta square t is for radial, I mean for cylindrical coordinates. Okay, the same thing you can find out for spherical coordinates also, and then you can start solving the, you can start finding out the temperature profile. But now we can just simplify it and move on. So if I consider a sphere, if this is r1, if the smaller radius is r1, if the outer radius is r2, and there is some thickness, and the thickness of this differential element is dr, suppose, and here to here it's suppose r is some arbitrary radius inside the sphere. So we can directly calculate what is the q. Q is given by minus ka dt dr. Here what is changing for this radial systems like cylinder and sphere, cylindrical and spherical systems, always it's the area which is changing. Okay, variable area systems. So it is, if we write it, a is, what is the area of a sphere? It is 4 pi r square, sorry, 4 pi r square. So how can we get the temperature profile? square. Just about the constant. T is constant, 4 is constant, 5 is constant. It's only the R. Why the area is changing? Because the radius is changing. So 4 pi a divided by q. Answer is T. So if you integrate it from R1 to R, maybe to till R2 also you can integrate. Then suppose in R1 the temperature of the this element is T1 and the outside surface temperature of the uh, sphere is T2. So if we integrate from T1 to T, and in this arbitrary R, the temperature is T, suppose. Okay. So what you'll get if you integrate it, you'll get 1 by R minus 1 by R from R1 to R minus 4 pi A divided by Q T minus T1. So what do you get? 1 by R1 minus 1 by R is equal to 4 pi K by Q T minus T1. So how do you get T from here?
And log is remaining.
Huh. Yes.
Direct we can take ln r1 by r2 1 by r1 minus r2 है ना तो
Yeah, that also
डायरेक्टली
you can do. This is just I want, yeah, you can, instead of this R you can take R2, and instead of T you can take T2 also. Directly you can integrate. But I just want to give a general uh, profile for this T. Later in the, again with this T also you can substitute this T with T2 and you can substitute R with R2. And now I just want to give a general formula for T. That's why I'm doing from T1 to T, from R1 to R. You can directly give R2 and T2 also, no issues. So if anyone asks you what is the temperature profile, so you, this is the temperature profile. I mean, if temperature profile means you are asked to find out what is the T, what is the generalized formula for T, and what is the generalized equation for T. So in is now if you want to calculate for 2 points R1 T1 and R2 T2, then just substitute this T with T2 and R with R2. You will get. So if you put here T2, then you get R2. Okay. Now what is the Q for this? T2 minus T1 divided by 1 by R2 minus 1 by R1 whole divided by 4 pi k. So whatever is in the below, if you get it delta t divided by something, so this will be the resistance to, okay. So T and R are always, I mean this, not T and R, this Q is equal to delta T by resistance, or resistance is equal to delta T by Q. Okay. So like this you get, so whatever is below the whole one is R resistance. So resistance is given by, in spherical system it is given by 1 by R2 minus 1 by R1 whole divided by 4 pi K. So we'll go to the this problem. The wall of a spherical tank of 1 meter diameter contains an exothermic chemical reaction and is at 200 degrees Celsius when the ambient air is at 25 degrees Celsius. So ambient air is at 25 degrees Celsius. What is the thickness of the urethane? Okay, the wall of a spherical tank is 1 meter in diameter. So this is 1 meter. Sorry again, this is the whole one is the diameter, right? So only this will be, only the radius will be 0.5 meter. So inside this spherical tank there is an exothermic reaction going on, and that inside temperature is 200 degrees Celsius. Okay, again this temperature is not the temperature of the uh, wall, spherical wall, but it is the temperature of the reaction going inside. So this is again T infinity, suppose 1, and the outside one is T infinity 2. So what thickness of the urethane foam is required to reduce the exterior temperature to 40 degrees Celsius, assuming the convection coefficient is 20 watt per meter square for both situations. This means the, the convection coefficient, that means the outside coefficient is H2 is equal to 20 watt per meter square Kelvin. Then what is the thickness of the urethane foam? So, so some foam or some insulation type of thing is wrapped around the sphere to reduce the temperature to 40 degrees Celsius. Okay. So if we draw the insulation, so this temperature will be 40 degrees Celsius. So they have asked to find out what is the thickness of this insulation, or what is the thickness of this foam. So what is the percent, and what is the also what is the percentage of heat rate achieved by using this insulation? So there will be some, because of this insulation there will be some reduction in heat loss. Okay, then so what is that percentage of heat loss also, that you need to calculate. Then properties are given this. So for cylindrical, for spherical, what we have seen is, okay, so first how to proceed this. This is a surface temperature. Now for sphere, what we have seen is this R is 1 by R2 minus 1 by R1 divided by 4 pi k. Okay, so there are two resistances. So first one is this this resistance due to this insulation. Okay, then another is resistance is the outside resistance due to the convection. So if I consider it as 1 for the insulation, it will come out it to be it's a conductive resistance. Okay, so 1 by R2 minus R1. So you don't know what is R2. R2 is the one which you have to find out. So R2 minus R1. R1 is 1 divided 0.5. Then 4 3.14 into K. K is how much? 0.026. How much do you get it? You will get some value for this. Okay, I'm not calculating. Since there is R2, just keep it as it is. R2 1 by R2 minus 1 by 0.5 divided by 4. Just calculate the below one. And another resistance is the resistance due to this convection, this outside convection. This is again for convection, it is simple 1 by just 1 by HA. So this A is due to the outer radius. So again 1 into H into uh, it's not 2, it is 4 pi r square. So it is approximately around 3.98 into 10 to the power minus 3 divided by R2 square. Okay, so this is the R total, RT suppose. So Q is also not given. So how will you find out in this case? How to proceed? So what happens in this case is whatever heat that is transported to this interface is the same heat which is transported to outside. Okay, the heat always remains constant. So you Ts minus, suppose it is T naught. So if you equate these two, you can find out what is R2. You'll get some quadratic equation of R2. So you just maybe by trial and error method you can calculate the R2, or in some scientific calculation also you can calculate the value of R2, because here the square term is there, so you'll get a quadratic equation in R2. Can you calculate how much is it? So Ts is 200, T naught is 40, T naught is 40, and T infinity is 25. And R1 and R2 are calculated before only. So everything you know, only R2 is you don't know what is R2, but you'll get a quadratic equation in R2, which you have to find out by some methods, some mathematical methods which you have followed previously during school days, or you can use trial and error, or maybe in calculator also you can directly calculate. So what have they asked? They have asked to find out what is the thickness. So this is the opposite of what is asked in the previous questions. In the first question, you calculated the outside radius, but now you got the outside radius, that is R2. So how you get the thickness? Thickness you just get by R2 minus R1. So R2 you will get around 0. Just check it later, okay? Just calculate and check it later. It will come out to be around 0.5135 meter. And R1 you know already, R1 is the 0.5 meter. So thickness will be 0.5135 minus 0.5. So it will come out to be 0.0135 meter, which is equal to 13.5 milliliter. Okay, this is the thickness. Just calculate it and check it later. I mean, check it how much, whether it is whether you are getting such values. Okay, then how will you find out next? What is the question? What is the percentage reduction in heat rate achieved by using the insulation? So first you have to calculate the heat rate without insulation, and you have to calculate the heat rate with insulation. So heat rate you will get by, if I I'll just take a new page. So you just have to substitute the values in the mm previous. This r2 value, this r2 value you can substitute in this first resistance and second resistance r2 here, and you can find out what are the resistances. And even here also you can find out, you can substitute and find out what is the capital R1 and R2. Then you can find out what is the total resistance. After finding the total resistance, I'm not calculating now, so directly I'm writing what is the total resistance. It will come out to be around 0.1779, and here you get, here you get around 10.91 kilowatt. Here you'll get around 0.99 kilowatt. So what is the percentage reduction? You'll get this to be around 91%. So you got how to do this. I'm telling you again how to do this. So here, since the Q is not given, you have to find out, but you are asked to find out what is the R, that is the outer radius of the sphere. But the Q is not given, so you cannot find out by using this formula, by finding the total R. I mean R1 plus R2 or R total. But instead what you do is that whatever heat is, suppose this is the, if I draw in planar, if this is the inner surface of the sphere and this is the insulation and this is the outer surface, I mean, or it is the air, ambient air. So what it is said that whatever heat is getting transferred to this, I mean getting transferred inside the insulation, that heat is getting transferred to the air. Okay, the same heat is getting transferred to the air. Okay, there is no heat loss in that. So what you will get, so whatever heat is getting transferred inside the insulation is given by this. That means the outside temperature of the insulation is 40 and the inside of the insulation is 200. So Ts minus T0, that means 200 minus 40 divided by resistance, the first resistance, that is resistance offered by this insulation. Okay, and this is equal to the heat transfer to the ambient air, that means this. So how will you calculate the heat transfer in the ambient air? That is the T naught minus T infinity divided by the resistance offered by the air. Okay, the convective resistance. So T naught is again, here it is 40 and T infinity is the 25. So as R2 is the resistance offered by the convection, that is 1 by HA R, sorry, A. So you'll get this. So with that equation, if you put all those, if you substitute the values, you get the value of R2. And here you get a quadratic equation. I have not written that equation, but you, if you solve this equation, you will get a quadratic equation in R2, and you can get the value of R2 just by doing some mathematical solving, and or you can directly calculate in the calculator. And then next they have asked to find out, okay, before that, the R2 is the total radius, okay, from center to the to the outer sphere. But they have asked to find out what is the insulation thickness, the thickness only. So for insulation, you have to just deduct the R1 from the R2, the total you have got. So that will give you the insulation thickness. And then next question, they have asked to find out what is the percentage heat reduction. Because of the addition of that insulation, some heat reduction is reduced. Okay, it's directly not getting to the into the air, but it is going through some insulation. So the heat reduction is reduced in this, heat loss is reduced in this case. So how will you find that? First, you find out the Q without insulation. Suppose you consider that there was no insulation at all. There was no insulation at all. So in that case, you have to directly consider this TS, that is 200, inside temperature 200 and the outside temperature is 20, 25 is already given here. Okay, and there is only single resistance, that is the outside air convective resistance. Okay, so that is what you have done in the this one. Okay, so the resistance is only the convective resistance. So 200 minus 25 divided by 1 by HA, it is 1 by HA. Okay, so A is given by 4 pi r square. For sphere, A is given by 4 pi r square and R is 0.5, and you can just calculate it to be around this. Then with insulation is what we have done in the previous slide. Okay, with insulation, that is total resistance. The resistance of the insulation will also come into picture, and the total resistance, if you substitute the values of RT, you will get the total resistance to be around this value, and the Q value will get around this, and the percentage reduction you can directly calculate from this minus this divided by the original, and you can get the reduction percentage. So could I explain you this problem? Hello, did you get this problem? Okay, so next one is, this is just an arbitrary some conical section. The diagram shows a conical section fabricated from pure aluminium. It is of a circular cross section. So they have not shown the cross section. They have given a side view. Okay, this cross section is having a diameter of d equal to ax to the power half, where a is equal to 0.5 meter to the power half. The small end is located at 25. This small end, it is located, this is, if we start calculating from here, so here to here it is 25 millimeter, and the large end is at 125 millimeter. Here to here it is 125 millimeter. The end temperatures are T1. For the smaller area it is T1, and for the larger area it is T2, which is 400 and 600 Kelvin respectively. And while the lateral surface is well insulated, lateral surface means the surface which is shown here, this is insulated. So calculate the heat rate given pure aluminium at 500 Kelvin they have given. Because usually here you don't need to calculate, but usually why 500 Kelvin is given, because the temperature at both ends are around 600 and 400 Kelvin. So you always, if the thermal conductivity is not given, if K is not given, then always try to find out the K at the average temperature. Okay, that means 600 plus 400 divided by 2 at 500 Kelvin, whatever is the thermal conductivity of the aluminium, of the whatever material, you should take that. Okay, that's why they have given it 500. At average temperature you always need to calculate. Okay, then so how do we proceed this? So here Q, just like we have solved for the spherical, we have just done a small derivation for the spherical like this one. Q, you have find out we have found out the Q, that is heat rate for the spherical system. So in this case also, just it is not a sphere, it's just some conical section. The same way you have to calculate. So Q is equal to minus Ka dt dx. And here the variable is again A. And why A? Because at different values of x, the area is changing or the radius is changing. So A is given by, is just a circular section. So it is given by uh, pi r square, right? Pi r square dt dt dx. But what it is given? It is given the diameter is given, right? So instead of r, you can write in terms of diameter also, minus k pi d square by 4 dt dx. Now this diameter is a function of x. And what is the function? D is equal to ax to the power half. And a is given as 0.5. So if I write ax to the power half whole square dt by dx. So what we get? X dt dx. Let's just calculate what is q in this case. Okay, it should be square. A square. Okay. Tell me which one is the answer. Substitute everything.
Ma'am, show the question. Show the question.
Are you able to solve? Okay, I'm. Did you get till this slide? Did you get?
Option
The option
A.
A. Yeah, option A is right. Yeah, right. Okay, we'll go to the next question. Okay, a spherical tank for storing liquid oxygen on a space shuttle is to be made from stainless steel of zero point 0.8. It's actually 0.08. Just correct it. It should be 0.08 meter. Outer diameter and 5 millimeter wall thickness. So what it has given? It's given a spherical tank. It has a thickness of 5 millimeter wall. This tank itself has a thickness of 5 millimeter wall. This is not insulation thickness, but this is thickness of the uh, tank itself. So delta T is given as 5 millimeter. That is 0.005 millimeter. And this is to be made from stainless steel of outer diameter 0.08. That means this whole one. This is 0.08 meter. So is outer radius, how much will it be? R naught is equal to 0.04 meter. The boiling point and latent heat of vaporization of the liquid oxygen are 90 Kelvin and 213 kilojoule per kg. So what is it carrying? So inside this is liquid oxygen. Okay, it is storing, or it is carrying storing liquid oxygen, and that liquid oxygen, it is at temperature, since it is fluid, so I'm denoting it as T infinity 1 is equal to 90 Kelvin, and the latent heat of vaporization, HFG. The tank is to be installed in a large compartment whose temperature is to be maintained at 240 Kelvin. So you can consider this whole slide as the large compartment. So that is very, very big compared to the tank. And what is the temperature maintained? It is maintained at 240 Kelvin. That means around 33 degrees Celsius, maybe 37 degrees Celsius, around 273 minus 240. Yeah, 33 degrees Celsius, that is the T infinity 2. Okay, this is the outside air. Find the minimum thickness in mm of thermal insulation layer that will maintain oxygen losses due to boiling below 1 kg per day. So there is another insulation layer which is surrounding. If I draw it with green color, so another a thermal insulation is given around the spherical tank to maintain the oxygen losses below 1 kg per day. Assume the conductivity of the steel as 9.2 watt per meter Kelvin and conductivity of insulating material. So in this question, If I redraw again properly, then there are this is R1, this is R2, this is R3. Okay, so R2 is the spherical tank actually, and R3 is the radius of the this insulation. Okay, outside insulation. So this spherical tank has a radius of, it is given already. So R2 is already given 0.4 meter, 0.04 meter, and the thickness of this spherical tank is also given. How much was it? Thickness was given to be 5 millimeter, 0.005 meter. Okay, so if thickness is 0.005, so R1 will be 0.04 minus 0.005, that is 0.035 meter. Okay, now you have to calculate what is R3, that is the thickness of the insulation or the radius of the insulation. They have asked to find the minimum thickness in thermal of the thermal insulation layer that will maintain oxygen losses below 1 kg per day. 1 kg per day means per second how much will you get? 1 divided by 24 into 60 into 60. How much will it be? 1 by around 86400 kg per second. Okay, so here again uh, there are resistances. Again you have to draw the resistance network here. This is one resistance, this is another resistance, then because of the fluid there is this one, you don't need to consider. For finding the R3, the conductive resistance is for sphere it was 1 by R2, 1 by R1 minus R2. By R1 is 0.035 minus R2 is 0.04 divided by 4. Steel, what is the K of steel? 9.2 watt per meter Kelvin. Since we are finding the resistance due to the steel, so you have to find out the resistance of the steel only, the conductivity of the steel only. So it will come out to be around, if you calculate it, just calculate it how much it's coming. Then another resistance is conductivity due to the this insulation. For this it is 1 by, since insulation is outer circle, it is R2 minus R3 divided by 4 by K of the insulation. K of the insulation is 0.4017. you'll get a value for this R conduction. I mean the resistance due to conduction of of the steel, but you won't get a value for this for insulation one because you don't know what is R. So R3 is, I mean the radius of the outer sphere is what you have to calculate. So again you'll get some algebraic equation, maybe algebraic or quadratic. You just solve and see how much it is coming. This RT is equal to R conduction steel plus R conduction insulation. Okay, this plus this. Then what will be the Q? TS2 and TS1, you know already. TS2 is 240 Kelvin and TS1 is 90 Kelvin. And how will you find out this Q? They have given you the latent heat of vaporization and they have given you how much mass it's getting lost, okay? Lost. So if you just calculate mass into the latent heat of vaporization, you'll get the Q, okay? So this will be around, you just multiply this with HFG. How much is HFG given? 213 kilojoule per kg. This is kg per second into HFG is 213 kilojoule per kg. If you convert it into joule, you will get 10 to the power, sorry, 10 to the power 3 joule per. This will get cancelled, this will get cancelled. So what value you get this is in watt, okay? You will get joule per second, that is in watt you will get. So that is that value I'm not calculating, just calculate and see how much is Q coming. Whatever is the value that will be in watt. Okay, and then here you know all the values except R3. Except R3 you know all the values. So from there you get to calculate R3. And how will you find out the thickness of the insulation? Just calculate R3 minus R2 and that will give the thickness of the insulation. Okay, we are running out of time. You just try to calculate this. Okay, maybe we'll solve this question in the next week. Two small questions I have. You can just finish it off. Efficiency of fin with insulated tip is. You can just tell which one is the option. Already, I mean this is a formula inside the textbook. I mean, even in the lecture also it's there. You can find which one is the efficiency of fin. Can you tell which one is the efficiency?
Option B.
Yeah, option B. Then quickly, okay, this is all the last question. Fins are used to increase the heat transfer from surface by increasing the temperature difference, increasing the effective surface area, increasing the convective heat transfer coefficient, none of them. Which one do you think is why are fins? Sir has already taught what are fins. They are extended surface. Extended, I mean, whatever is the surface, from there you extend some more surface, and then you can increase the heat transfer. So why they are used to and how they're used to increase the heat transfer, it is given from this option. Which one do you think is the option? Already in the name itself it's there, extended surface.
Option B.
Yes, so by increasing the effective surface area, the area, because of that extended surface, the area of the total surface area available for that heat exchange, it increases. Okay, so like that you can increase the heat transfer. By all these ways also you can increase heat transfer, but fins are used to increase heat transfer by only increasing the surface area. Okay, then this is the last question. So how much is the time? Okay, you can just tell me quickly, have you understood this problem or not? Rest, this only one question is left, which is of fins. We will solve in the next class. Just tell me quickly, you have understood this equation, this problem or not? You have got it? Okay, you just try. Okay, tell me how much values and all you get here for R3 and the value of this thickness of the insulation. Okay, fine, right? And then you have any more questions you can ask. Okay, thank you for today.